mean value theorem for derivatives, right? The instantaneous rate of change is equal to the average rate of change as long as the function is continuous and differentiable on that closed interval from a to b. All right, so let's show that x squared satisfies the hypotheses of the mean value theorem for the closed interval from 0 to 2, and then we'll find the solution c on that interval. So what's the first thing we need to do if we're going to show that this function satisfies the mean value theorem? We need to state the continuity, and then after that we need to state the differentiability, right? So f is continuous, and why is f continuous on 0 to 2? It's continuous because it's a polynomial, right? Okay. And we also know that all polynomials are differentiable, but we could also just say f prime, which equals 2x, exists on the open interval 0 to 2. Once again, because it's a polynomial. Or we could just say that we know the derivative exists because the derivative of a polynomial exists. So good with the continuity and the differentiability. All right, so from there, what are we going to do? We need to find what f of 0 and f of 2, right? Our average rate of change from 0 to 2. So f of 0 is 0 and f of 2 is 4. So our average rate of change should be 4 minus 0 over 2 minus 0. And we know that that equals 2. And what should this equal? It should equal f prime of c. And it should equal the instantaneous rate of change. And so f prime of c is 2c. And so our c value is 1. Everybody good with that? So just to take a look at it, if we have x squared, the slope of the line that is secant to this function between 0 and 2, we said was 2, right? So that should be y minus 4 equals 2 times x. That didn't, or should that be y minus 4 equals 2 times x minus, x minus 2, not just x. And then the other one that goes through 1 should be, the point's 1, 1, so it should be y minus 1 equals 2 times x minus 1. And we can see that obviously they have the same slope because we put them in point slope form. But we can see that one is the tangent line and one is the secant line that goes through the origin in the point 2, 4. Everybody good there? Any issues with that? All right, let's talk about these two functions on the interval from -1 to 2. And neither of these will satisfy the hypotheses of the mean value theorem. And so I'd like you guys to take a quick look at that and figure out why they don't satisfy the hypotheses of the mean value theorem on -1 to 2. So for the first one, is this function continuous from -1 to 2? Can I plug any value in there between -1 and 2? Should be able to. But what about differentiability? What's the derivative of this function? F prime of x should equal what? 1 over 2 root x squared times the derivative of root x squared. I'm sorry, times the derivative of x squared, which is 2x. And what does that give us here? We have an issue with our differentiability, right? It's not differentiable where? Not differentiable at x equals 0. So mean value theorem doesn't apply for this one. And what about the other one over here? What's the limit as x approaches 1 from the left of f of x? As we approach 1 from the left, we should be looking at the top piece of it here, right? Which should be as we approach 1 from the left, what do we get? 1 cubed plus 3 is 4. And if we take a look at the limit as x approaches 1 from the right, we should be looking at the bottom piece. What does that equal? 1 squared plus 1 is 2. And so because those limits are not the same, the function is not continuous at x equals 1. Everybody good there? Everyone good? Yeah? All right. I think we're good. Let's just move on and talk about increasing and decreasing functions. Everybody good with the mean value theorem? Pretty straightforward. I hope. Yeah. All right. So what does the derivative tell us about a function? So first off, if the derivative is positive, then we know that the function increases on whatever interval that the derivative is positive. And if the derivative is negative, we know that the function decreases on whatever that interval is. You'll probably remember I made a big point about this last year for those of you that were in my class last year. But whenever the College Board asks you to talk about when a function is increasing or decreasing, they always want you to use closed brackets on it, even though that doesn't really make a lot of sense when we have a turning point or something. But you always need to use closed brackets for increasing and decreasing intervals. And so why is this true? If the derivative is positive, that means that the slope of the tangent line is positive, right? And if the slope is positive, that means the function should be going up, right? The f prime is positive, and if f prime is negative, and the slope of the tangent line is negative, and if that slope is negative, it should be going down. All right, everybody good with that? You'll want to know and memorize that. All right, so we talk about local maxima and minima. There's a lot of words here, but you guys know that if the derivative goes from positive to negative, right? If f prime goes from positive to f prime being negative, that means the function goes from increasing to decreasing. We get a local max. And vice versa, if it goes from decreasing to increasing, then we're going to have a local minimum. We can't just assume that a place where we have a critical value, and remember that a critical value, right, a critical value is a place where f prime is equal to 0 or f prime is undefined. We can't just assume that there's a local max or a local min there. We have to check for a sign change in the derivative. Yeah. And the same rules apply at an endpoint. If we increase from an endpoint, then this endpoint is a local min. And if we decrease from an endpoint, this is a local max. Same thing on the other sides. For a right endpoint, you can do the same thing. I think conceptually that's pretty easy. But the big point here is that remember that critical values are places where f prime is 0 or where f prime is undefined, and that just because you have a critical point doesn't mean there's a local max or a min. You have to check for the sign change of the derivative, right? So remember that if there's no sign change, there's no local extreme at that value. Everybody good with that? All right. Rolle's theorem. Hopefully you're familiar with Rolle's theorem also. Rolle's theorem is just a special case of the mean value theorem. Right? So this is a special case of the MVT where f of a equals f of b. Right? If f of a equals f of b, then what does that tell you about the average rate of change? That tells you that the average rate of change should be zero. And that would tell us that the derivative equals 0, at least one place on that interval. Tells us there's at least one critical value on that interval. So we should be able to apply Rolle's theorem, the special case of the mean value theorem, anytime that f of a equals f of b for a continuous differentiable function. So let's take a look at this one. 4x squared minus 20x plus 29 on the interval from 1 to 4. So first off, f is continuous. Why is f continuous? Because it is a polynomial. And we can also say and differentiable. We'll just say that for the same reason, because it's a polynomial. And then what do we need to show about f of 1 and f of 4? We need to see if f of 1 is equal to f of 4. So what's f of 1? F of 1 is 4 minus 20 plus 29. And what's f of 4? F of 4 should be what, 64 minus 80 plus 29. And it looks like both of those equal 13. So we know that f of a is equal to f of b, which tells us that the average rate of change is 0, which tells us that there is a place on the function where the derivative is equal to 0 between 1 and 4. So on the interval 1 to 4, there exists a C such that f prime of C is equal to 0. And what's f prime of C? Give ourselves a new page here. F prime of C is equal to, what was it? Now I don't even remember what that function was. Should be 8c minus 20. Everybody agree with that? Hopefully. Which tells us that c equals 20 over 8, or 5/2. Everybody good with that? And we could look at the graph of this if we wanted to. We had what, 4x squared minus 20x plus 29. And if we look at 5/2 right here, 2.5, that's where our local minimum is. That's the place where our derivative is 0. It's where we have a horizontal tangent line. Everybody good with that? Any issues, any problems? Everyone okay? Y'all still awake? Oh, good. All right. We talked about concavity. We know that if the second derivative is positive, then the function is concave up on that interval. And we know that if the second derivative is negative, the function is concave down on the interval. And we, I hope, remember what concave up and concave down look like, right? Concave up and concave down. And so we can also say that if the derivative is increasing, the function is concave up, and if the derivative is decreasing, it's concave down. And that should make sense, because if the derivative is increasing, so if y prime is increasing, that tells you that its derivative, y double prime, must be positive. And if y prime is decreasing, then that tells us that y double prime is negative. Its derivative is negative. So remember that we can have a point of inflection anytime the second derivative equals 0, or when the second derivative is undefined. But just because the second derivative is 0 or undefined does not mean that there is a point of inflection. You have to check and make sure there is actually a change in concavity. Everybody good with that? This should all be review. And then we can also use a second derivative to determine if the function has a local max or a local min at a place where the derivative is equal to 0. So our second derivative test says that if f prime is 0 at some value c, and f double prime is negative, then f has a local max at c, which should make sense, because if f double prime is negative, that tells you that the function is concave down. And anywhere on there where the derivative is equal to 0, if it's concave down, it's going to have to be a local max. And f double prime being positive tells us it's concave up. And if we think about that, anywhere where the derivative is 0 on a concave up function is going to be a local min. Everybody good with that? So sometimes it might be quicker and easier to use the second derivative test to determine if something's a local max or a local min, rather than doing a sign chart with your first derivative. All right. So here's what we're going to try and do. We're going to find all of the local extrema, all the intervals where the function is increasing and decreasing, all of the different intervals of concavity, and any points of inflection that we might be able to find on this function, f of x equals x cubed minus 12x minus 5. What are we going to do first? First thing we should probably do is take a derivative, right? What's f prime of x going to equal? 3x squared minus 12. And first we're going to see when this equals 0. When does that equal 0? When x is plus or minus 2. And then we'll also see when is f prime undefined, and we'll say that f prime is undefined never. Why is it never undefined? Well, because it's a polynomial, right? Polynomials exist for all real numbers. Okay? So we have two critical values, positive 2 and negative 2. How are we going to determine if the function's increasing or decreasing, and whether we have local maxes or local mins? Sign chart, exactly. So we're going to make a sign chart. We're going to put on negative 2. We're going to put on positive 2. We can take a number between negative 2 and 2 and plug it in here, like 0. If I plug in 0 to my derivative, remember that you plug it into the derivative. This is a sign chart specifically for the derivative. Then we get a negative. which tells us what? If the derivative is negative, the function decreases. And if we plug in something greater than 2, like 1,000, this is clearly going to be positive, and it will increase. And if we plug in something less than -2, like -1,000, we square it, it becomes positive, and it's still positive. And so therefore the function increases from -∞ to -2. Everybody good there? Tells us that we have a local maximum at -2 and a local minimum at +2. So far, so good. We'll write all the stuff out at the end once we've done all the work. All right, next thing we'll do is look at f double prime of x. What's f double prime? Derivative of f prime, which should just be 6x. And when does 6x equal 0? When x is 0. And when is this undefined? We'll say that it is undefined never. Once again, because that's a polynomial. So it's never undefined. And we'll make a sign chart for our second derivative. Okay. And if we plug in something positive to our second derivative, we get a positive. And if we plug in something negative to our second derivative, we get a negative, which tells us that we're concave down here and concave up here. And since there was a change in concavity at x equals 0, it tells us we have a point of inflection at x equals 0. Good or no? Any questions or issues with this? Pretty straightforward, I hope. All right, so when is this function increasing? We know it's increasing from -∞. Remember that the infinities always go in parentheses, to -2. Since it's an increasing or a decreasing interval, we have to put the whole number, the real number of values into brackets, even though that doesn't make a lot of logical sense. And then union 2 to infinity. And then where is it decreasing? It's decreasing on this interval from -2 to 2, and we still have to put those into brackets. Everybody good with increasing and decreasing intervals? All right, what about when we are concave up? Concave up should be from 0 to infinity, and concave down, and in these ones we can use the correct parentheses on it all, -∞ to 0. Everybody good with that so far? All right, I assume everyone's good based on the silence there. Either that or you've all disappeared and gone to sleep and not paying any attention. All right, so what about a local max or a local min? So our local max we know occurs at -2, but if we're asked what are the local extrema, the local extrema is actually the y value. X equals -2 is the location where it occurs. So we have to figure out what is f of -2. So what's f of -2? It's -8 plus 24 should be 16 minus 5 is 11. So we have a local max of 11. We could say that it occurs at x equals -2, but the place where it occurs is insignificant to what they're, or it's irrelevant to what they're asking. They're asking, what is the local extrema? It is 11. It occurs at x equals -2. Sometimes they'll ask where does it occur. Sometimes they'll ask for the coordinates of that point. So just make sure you answer what they're actually asking. What about a local min? Plug in our x equals 2 value. So we'll find f of 2. which should be 8 minus 24, which is negative 16, minus the 5 is negative 21. So negative 21 at x equals 2. Everybody good with that? Okay. And then our point of inflection, we'll need to find f of 0. F of 0 is equal to negative 5. And so we will say that we have a point of inflection is the point 0, negative 5. And I believe that should have answered all of the questions that we were asked to answer. Local extrema, intervals where it's increasing and decreasing, intervals of concavity, and points of inflection. Any issues there? And if we want to take a look, here's our graph. You can see it looks like 2, negative 21 and negative 211. We can see that we are concave down until we get to right here at 0, at 0, negative 5, where we have that y-intercept. And then we switch to concave up there. And we've got our increasing interval from negative infinity to negative 2, decreasing from negative 2 to 2, and then increasing again from 2 to infinity. Everyone good? All right, I think we had done at 10:04. Is that right? I think that sounds right. So probably don't have time to get through a whole nother one of these, especially one that's a little more complicated. So we'll focus on that on Monday, and we should get through everything that we should have done today that we didn't, because we didn't. We should get through it all on Monday, and then we'll get into some of the parametric stuff on Monday also.